All right, continuing in section 5.2 with some examples where we're going to actually calculate the approximate area under our curve, right? So go through, we've talked about now the idea of the integral and what that represents ultimately, right, area under the curve. And we're going to get into the evaluation of integrals going forward. But what I want to look at first is just a couple of examples where we can use those rectangles that we were talking about, form subintervals, form the little rectangles under our curve, and use that to calculate or at least approximate the area under our curve. Right, so take you through that a couple times. Now we're going to use the calculator to do most of the calculation here. So have your calculator handy. I'll show you how to do that. This is a little bit of grunt work. It's one of those cases where you're going to have to do some calculations, but we're going to streamline it. We're going to use the calculator to do most of that for us, so you don't have to spend a bunch of time trying to calculate this stuff by hand. All right, so here's what I've got. I've got the function f of x equals x squared minus 1. And I'm looking at that function over the interval from 0 to 3. And we're going to evaluate the Riemann sum with n equal to 6. So that's our number of subintervals. Taking the sample points to be the right endpoints of those subintervals. Right? So we said we can use any value or x value in each subinterval to calculate the height of our rectangle. In this case, we're going to use the right endpoints as our sample points. Right? And then we'll answer the question, what does the Riemann sum represent? And now drawing a diagram, I'm not going to ask you to do that specifically on a test, so when you're doing your homework problems, don't worry so much about drawing the diagrams. I'm more interested in the actual calculation. All right, so what do we do? Where do we start? Well, first thing, if I'm going to form my rectangles, right, I need to know the width of my rectangles, so I know where where each of those subintervals is going to end. So I've got 6 subintervals. So the first thing I'll do is calculate delta x, right, the width of each rectangle. Now remember, we had a formula for that. Delta x is b minus a over n. Okay. So we take the width of the interval. Now the interval, remember, here is going from 0 to 3, so a is 0 and b is 3. So I take the width of the interval, 3 minus 0, divide by the number of subintervals, n. I get 3/6 or 1/2, and that is delta x. Okay. So there's the width of each of our subintervals, right, each of our rectangles. And so what I then went ahead and did, I drew the diagram on the left. Here's the graph of the function just to give us a visual. Now again, you don't have to have the graph to do the calculation, but it gives you a little bit of a visual of what we're doing, right? So here's our function f of x. And so with the delta x of 1/2, I went ahead and calculated or determined the endpoint of each of our subintervals. So the right endpoints, remember, I'm starting at 0. The width of the rectangle is 1/2, so the first subinterval would end at 1/2. So that's going to go from 0 to 1/2. And then at x equal to 1/2, I use that to calculate the height of that rectangle. Now this is one of those cases where we talked about earlier, where the area of that rectangle would actually be negative, because the height of the rectangle, because f of x, f of 1/2 is a negative value, if you calculate the area of that rectangle, it's going to give you a negative value because it lies below the x-axis. Okay. The next subinterval would end at 1, because all I'm doing again is adding delta x to get to the end of each of our subintervals. So if the first one ends at 1/2, the next one add 1/2, and I'm at 1. Now notice in this case on the diagram, there's the second subinterval from 1/2 to 1. F of 1 equals 0. So that subinterval, that rectangle, has no height. So when we talk about its area is actually 0 because there's no height to that particular rectangle. The next subinterval, add 1/2 again, and we're at 3/2. So then I use 3/2 to calculate the height of that rectangle. The next one would end at 2. So all we're doing is adding delta x each time to get the endpoint of each of our subintervals. And that's where we calculate the height, because as requested, we're using the right endpoint as our sample point. So our next one ending at 5/2, and then the last one ending at 3. And so then we've got each of those rectangles, right? And we can calculate the area using those right endpoints. So f of x sub I, x sub 1/2, x sub 1, x sub 3/2, x sub 2, etc., times the width, delta x, which is 1/2. So I'm calling this r sub 6 just because we're using the right endpoint with 6 subintervals. Again, I'm that, not that big of a deal, but it's nice to specify. That way we know exactly how we're choosing the endpoints. So r sub 6 is the sum as I goes from 1 to 6, right, because we got 6 subintervals, of f of x sub I delta x. And again, delta x was 1/2, so I'm going to plug that in. So I've got the sum as I goes from 1 to 6 of f of x sub I, which that changes from subinterval to subinterval, times delta x, which is 1/2. All right, so this is kind of going back to the notation that I explained earlier. So that sum notation means I would plug in, first of all, I equals 1, so x sub 1, which is the right endpoint of our first subinterval, which is 1/2, so f of 1/2 times delta x, plus f of x sub 2, the second sample point, right, which is 1, times delta x, plus f of x sub 3, right endpoint of our third subinterval, times delta x, etc., etc. Fourth subinterval times delta x, fifth subinterval times delta x, and finally we get to the last right endpoint of our last subinterval, which is b, right, the right endpoint of our interval, delta x. But if you notice, each one of these calculations, as we kind of noted before, is being multiplied by delta x, right? So it's f of x sub 1 delta x plus f of x sub 2 times delta x plus f of x sub 3 times delta x, etc., etc., etc. So there's a common factor of delta x, or 1/2 in this case. So we factor out the 1/2. And I'm left then with f of x sub 1 plus f of x sub 2 plus f of x sub 3, etc., etc., up to f of x sub n. And then if we calculate each of those function values and take their sum, multiply that times 1/2, you're going to get well, not approximately, it actually comes out to an exact value in this case, 8.375. Now remember that represents the net area from our previous discussions. When we talk about the area under the curve, this is the approximation of the net area under the curve. It takes into account the fact that this first rectangle has negative area, the second subinterval has 0 area, and then we have each of the other subintervals that have these positive areas. Now, I don't need you to calculate each of those areas individually. I'm going to show you how to do this on the calculator, streamline this process, do this as one calculation, and save us a bunch of time. But all we're doing is, ultimately, this calculation. So I'm taking delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3 up to our last subinterval, okay? Now, how we're going to do this on the calculator, right? So this is just really a calculation. Go into your y equals editor, plug in your function, right? So put in f of x, so y equals x squared minus 1 in this case. Then go back to your home screen, plug in delta x, which is 1/2, and open a parentheses. Right, so basically I'm just mirroring what I have up here. So 1/2, open a parentheses. And then we need to plug in each of our function values. So to do that, since we've already put f of x into y equals, if you hit the vars button on your calculator, and then scroll over to y vars, so hit the vars button, scroll over to y vars, and notice it's already selected on function, so just hit enter. Didn't want that. Hit enter. It brings you to this screen, which says y1, y2, etc., etc. Well, we put our function into y1, so that's what we want. So we're just going to hit enter again. All right. And it's going to bring you back to the home screen, and it'll have a y1 up there. All right, so let me recap that real quick. So we put our function into y1, We went back to the home screen. We put in delta x, open the parentheses. Then we do vars, y vars, and hit enter twice. And that will bring you back to your home screen, now with the y1. You will then input your function value, right? So what we're doing is we're telling this calculator, I want to evaluate y1, which is our function. And then we plug in our function value, which the first one is 1/2. Now notice I have 1/2 in parentheses. Don't forget to do that, okay? I don't care if you're just plugging in a single value. Even if I was just plugging in 1, you would put 1 in parentheses. So I'm telling the calculator to evaluate y1 for x equal to 1/2. Plus, and then from here, we're just going to repeat the process for each of our calculations. So that's our f of x sub 1 delta x times f of x sub 1 plus f of x sub 2. So just repeat the process. Vars, y vars. It'll bring you back to the home screen, and then put 1 in parentheses. Plus, and then repeat. Vars, y vars. It'll be back at the home screen, y1. Enter in 3/2 as our next function value. Plus vars, y vars. Brings you back to the home screen, y1. Enter in our next value, which would be 2. Okay, and then you just repeat that until you have entered in all of your function values, the last one being 3. Right, so it's just a repetitive process, and once you do it a couple times, it's pretty quick, right? So again, we start with 1/2. There's our delta x. We put our function in y1. Delta x is 1/2, open parentheses, and then after that, it's just vars, y vars, enter in each function value in parentheses. So vars, y vars, vars, y vars, vars, y vars, until you get to the last one, which our last sample point was 3. Now, once I finish with that one, don't forget to put in this last parentheses, which is closing up the parentheses that we opened back here, all right? So don't forget to do that. You may end up with an error there because of the lack of the closing parentheses. So once you've entered in all your calculations, and then just hit enter. And there's the value, there's the calculation. And if we need to approximate that, whatever number of decimal places are specified, this one actually gives you an exact value of 8.375. Okay? And so that's our approximation to the area under this curve, x squared minus 1, using 6 subintervals, right, n equal to 6, and choosing the right endpoints to be the sample point of each subinterval. Okay. I have another example for us. When we had that earlier discussion about, choosing the sample points, we did the left endpoint, we had the right endpoint on the graphs. And remember, I also showed you one where I chose the midpoint. And we said it looks like the midpoint probably gives you the best approximation because it kind of splits the difference between the over and under approximations. So we're going to call this the midpoint rule, where we use the midpoint of each subinterval as our sample point. So I'm taking the integral from a to b of f of x dx being approximated by the sum as I goes from 1 to n of f of x sub I bar delta x, where x sub I bar represents the midpoint of your subinterval, right? And this is notation. You see this used like in statistics, where x bar notation, we call it. We use that to represent an average or a mean. In this case, we're using it to represent the midpoint of a subinterval, which is the average between the left and right endpoints of that subinterval, right? So again, it's delta x times f of x sub 1 bar plus f of x sub 2 bar plus f of x sub 3 bar, etc., up to x sub n bar. But it's still the same notation as before. It's still f of x sub I times delta x. We're just specifying x bar because we're using the midpoint. So delta x is still b minus a over n. Nothing changes there, the width of our subinterval. And then here's x sub I bar, the midpoint, which, like I said, it's really nothing more than the average of the two, the left and right endpoint. If I take the sum of those two, multiply by 1/2, I get x sub I bar. but ultimately it's just the midpoint of that ith subinterval. All right. So for example, let's use the midpoint rule to approximate the integral, this one from 1 to 3 of x squared times e to the x dx with n equal to 4 in this case. So delta x, b minus a over n, limits of integration, b minus a, 3 minus 1 over 4. Now here again I have 1/2, as with the previous. Nothing special about that. Just happens to be delta x again. So then we need to define our intervals, okay? So if I start at a, the left endpoint of our interval, which is 1, and add delta x to that, right, delta x which we just found to be 1/2, so my first subinterval would go from 1 to 1.5, or 1.5. The second subinterval would go from 1.5 to 2, right? All I'm doing again is just adding 1/2. That's delta x, the width of the subinterval. The third subinterval would go from 2 to 2.5. And then the fourth subinterval from 2.5 to 3. Now that's all we were requested here, n equals 4. So there are my 4 subintervals. I ended up at b at 3 with the endpoint of my fourth subinterval. Now the sample point in this case is the midpoint of each subinterval. Now how you calculate that, there's a lot of different ways that can be done. So you can use the formula that I gave you above where you can add the 2 endpoints and divide by 2. Or again, all I need to know is what is the midpoint in this case between 1 and 1.5. And that would be 1.25. So I'm going to call that x bar sub 1. It's the midpoint of the first subinterval. Now, once you find the first one, then to get the rest of these, again, all you have to do is add delta x, because remember, each subinterval has the same width. It's delta x. It's 1/2 units apart from endpoint to endpoint. So that should be the same distance from midpoint to midpoint, right? So once you find your first midpoint, then all you need to do is add delta x to get each of the subsequent midpoints as well. So 1.25 plus 1/2, or plus 0.5, would give me 1.75, so that's x bar 2. Plus 1/2 again, or plus 0.5, would give us 2.25, that's x bar 3. And then plus 1/2, or 0.5 again, gives me 2.75, which is the midpoint of our fourth subinterval, x bar sub 4. Right? So instead of necessarily having to go into each interval and do the calculation, you could just find the first one and then add delta x to get each of your subsequent midpoints. Now once you have that, then we're back to exactly what we did in the previous example. So now I'm looking at the integral from 1 to 3 of x squared e to the x dx being equal to the sum as I goes from 1 to 4. Now if we want to use a notation like we did before, remember the other one I called r sub n because it was the right endpoint, so maybe we could call this m sub 4 because it's using the midpoint with 4 subintervals. Again, not such a big deal. I don't care if you don't call it anything. But it's the sum as I goes from 1 to 4 of f of x sub I bar delta x because we're using the midpoint. All right, so that's my reason for using that notation. And again, you don't even have to write this when you do your calculations. I mean, all I want to see is, I would want to see this, because you need to tell me what delta x is and you need to show me what you're plugging in, so I want to see these guys. I want to see your intervals, your subintervals, and I want to see your sample points from each subinterval. That's required. And then you can jump down to this and show me what you're doing for your calculation, and then you can plug that into the calculator just like the previous example to get your approximation. All right, so we put y1 equal to x squared e to the x, so I would go into my y equals editor, plug in our function, and then back to the home screen, and then follow the process with the previous one. All right, so we put in 1/2, open parentheses, and then we do the vars y vars. All right, so vars y vars 1.25 plus vars y vars 1.75, etc., etc. In this case, we only have 4. Hit enter, And we've got approximately 94.703. I just rounded this one to a few decimal places, is what you should get. Okay? And that's it. I mean, so I'm going to give you one of these on your next test where you're going to do an approximation with one of these methods, whether we choose the right endpoint, left endpoint, midpoint, and you're going to see those in the homework. And this is what you have to absolutely show me. So you'll need to see the subintervals, what I have circled with the sample points, and then where I have the arrow with your calculations, and then your final approximation. Okay? Now, the rest of this section really just talks about some properties of integrals. So see, these are some of the things that we'll bring up as we go forward and talk more about the integration process, right? And, so some of the properties that we use or are allowed to use to evaluate integrals. Properties of the definite integral. Now, notice we're calling this the definite integral because the reason we're using that terminology, we have limits of integration. In other words, I know I'm integrating from A to B, or in this case, B to A. But because we have limits of integration, we call this a definite integral. We can actually calculate the area under that curve, as opposed to an indefinite integral, right, that we'll talk about later. All right, so for the definite integral, now notice with this one that I just highlighted, it's the integral from B to A. Think about this. If you were to calculate the area under the curve, remember the distance from A to B, that's the width of your interval, where A is less than B. Right? Remember, we did have that back in the original definition. We said that x goes from A to B, okay? So A is by default smaller than B. It's your left endpoint. So here what we're doing is we're integrating from the upper or larger value, the right endpoint, to the lower value. So we're actually integrating here from right to left. Right? We're integrating this way. So what does that mean in terms of the value? Well, now delta x, being I'm going from B to A instead of A to B, delta x would end up being negative, right? Because we're measuring the width from right to left, it's going to give us a negative value. So the integral from B to A of f of x dx, I'll get the same value as I would the integral from A to B of f of x if I integrated from left to right, but it's going to be the opposite because delta x there is negative. Now, in terms of the actual calculation, it doesn't matter how you do it. You can do it from right to left. You can do it from left to right. Irrelevant. You're still going to get the same value. But oftentimes what we will do is if I have an integral where I am integrating from right to left, we rewrite it as the integral from left to right, but we have to change the sign to counteract the negative delta x, right? So, as we get into some other examples, I'll mention this again, but ultimately, so do I have to do that? No, but a lot of times we do it just because it looks nicer to integrate from the smaller to the larger value. Okay? All right, so the integral from B to A of f of x dx equals the opposite of the integral from A to B. So in other words, if you reverse the limits of integration, you change the sign of the integral. That's the bottom line with that. The next property, the integral from A to A of f of x dx equals 0. Right, so if my left and right end point of my interval are the same, right, I'm going from A to A, I haven't gone anywhere, right? So my delta x, the width of our interval, is 0. And if delta x is 0, then, right, the width times the height would be 0. I don't care what the height is. So the integral from A to A of f of x dx equals 0 because the interval has no width. Other properties of the integral from A to B of a constant, the interval from A to B of c dx is equal to c times b minus a, right, where c is a constant. And that would be a case like, remember we talked about constant functions? I'm going to look at this before I look at that. I just thought about putting this graph up. So let's say I have a constant function, right? So here's our function f of x equals c. And if I integrate that function from A to B, right, I'm calculating the area under that curve from A to B. Well, because c is a constant function, then what we actually have formed is just a rectangle, right? Where the height of the rectangle is whatever c is, And the width of the rectangle is the distance from B to A, right? So B minus A. So there's our width times our height, and our height is C. So for a constant function, the integral of a constant function is simply the constant times the width of the interval, B minus A. Get this done. Okay. Yeah, that's good for now. I thought about something else, but that's good for now. Number 2, I've got the integral from a to b of f of x plus g of x dx is equal to the integral of f of x plus the integral of g of x. In other words, just like a derivative, right? Maybe we had the similar property for derivatives. The integral of the sum of functions is equal to the sum of the individual integrals. So in other words, it allows us to integrate term by term. Just like differentiation, we could differentiate the derivative of a sum is equal to the sum of the derivatives. Same thing is true for integrals. So the integral of a sum is equal to the sum of the integrals. I'm going to go down to number 4 because similarly, the integral of a difference, so we've done 1, we've done 2. The integral of a difference is also equal to the difference of the integrals, right? So basically, number 2 and number 4 allow us to integrate term by term. But notice there is no product integral, right? Just like with derivatives, remember the derivative of a product is not the product of the derivatives. We had a whole product rule that we had. Same thing was true with quotients. We had a whole quotient rule that we had to follow. Well, with integration, that's also true. So note it that the integral from a to b of f of x times g of x is not equal to the integral of f of x times the integral of g of x. So it works for sums and differences, but it does not work for products and quotients. There's a whole big process that we have to go through to integrate the product of functions. And this is one of the first ones that you look at in Calc 2. And it's one of the more difficult, I guess, challenging processes to integrate a product. Okay, so that's a Calc 2 topic. We're not going to see that come up in this case. Number 3 is the integral of a constant times a function. And just like with, again, differentiation, remember the derivative of a constant times a function is the constant times the derivative. Likewise, for integration, the integral of a constant times a function is equal to the constant times the integral. So, and especially probably more so here than with derivatives, if your integrand is a constant times a function, it's oftentimes more convenient to go ahead and pull the constant out of the integral and then just work with integrating or finding. Ultimately, we're going to see the antiderivative of our function. Okay, so this is one we tend to use in a lot of cases, just because if you get that constant out of the way, it makes the integration process a lot easier. We didn't bother with that as much with derivatives, but we tend to make use of that a lot more here with integration. Number 5 deals with what we call adjacent integrals, and this should make sense, if you think about the context again. We're saying that the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So notice this first integral starts at a, ends at b. The second integral starts at b and goes to c. This is equivalent to the integral from a to c of f of x dx. So basically what we're looking at is adjacent integrals. But if you remember, again, what does the integral calculate? It calculates the area under the curve. So if I calculate the area under this curve f of x from a to b, and I calculate the area under f of x from b to c, then I can just add those two areas together, right? Where we actually use this more so is in the opposite direction, right? Where we start with this integral, and maybe we need to break it up into adjacent integrals. So that would be a case like where maybe you have some point of discontinuity. Remember we mentioned earlier, if we have a fixed number of jump discontinuities, we could still calculate the integral. But what we would have to do is something like this. We would have to break the integral up at that point of discontinuity, right? And there's other reasons we would do that, as we will see going forward. So this is something, again, I'll mention to you. Adjacent integrals, mainly from the aspect of taking an integral and breaking it into smaller integrals. All right, so there'll be reasons that we do that. Some comparison properties. Again, I think these should, for the most part, make sense. That if we have a function f of x, or actually this is something we mentioned in our earlier discussion, if our function f of x is always positive for our integral from a to b, then the integral from a to b of f of x would also be positive, right? So that goes back to that very first example that I showed you in this section from our summary of 5.1, where the function was entirely above the x-axis, so we would say that the area under the curve would be positive as well, right? Again, number 7, I think, makes perfect sense, that if I have a function f of x that is greater than or equal to some function g of x over our interval from a to b, then the area under the curve of f of x should be greater than or equal to the area under the curve of g of x, right? So if f of x is greater than or equal to g of x, then the integral from a to b of f of x is going to be larger than the integral from a to b of g of x. And if you think of it in the context of area, that should make perfect sense. The last one, number 8, if I have a function f that lies between two constants, call them little m and big M. So I have a constant little m where my function value for f is always larger than that, but it's always smaller than the constant big M across our interval from a to b. Then the area under that constant function m, and that's what we mentioned back in that earlier with the rectangle, right, with the earlier integral of a constant, the area under our curve f of x should lie between the area under little m and the area under big M, right? And again, that just goes back to, like we mentioned before, under the constant function m, right? So the area under m would be this rectangle. Calculate that area. The area under big M, right, would be that rectangle. And since our function f lies between little m and big M across our interval, then the area under the graph of f would fall somewhere between the area under, or the area of that smaller rectangle and the area of the larger rectangle. Okay? And so that kind of goes, when we talked about at the very beginning of this section where I did the little rectangles and we showed that, when we used the left end point, I think our rectangles were all below the graph of our function. And when I used the right end point, they were all above. So I was able to show that the area under our curve lied between those two values, right? So that kind of idea. But I think this is intuitive when you see it graphically. It makes perfect sense. But it's just maybe the notation of what that means. Okay? All right, that's it for that section. And as we go forward, we're going to actually then talk more about how do you actually evaluate the integral. And that's where we're going to go back to the idea of the antiderivative and bring that into play. All right, that's it for this section.